Hello everyone. Let's continue with our discussion on flight dynamics, which is relevant for flight control design and which we will use it subsequently in this course especially. So, last lecture we have derived point mass equations in various assumptions and followed by 6 degree of freedom equations where we have derived the dynamic part of the thing, and then we will continue further on this particular lecture and try to finish it off. I try to give a complete overview of this dynamics actually. So, this 6 degree of freedom model, what we discussed last class is we essentially try to find a relationship in two coordinate systems. One is inertial frame, which is you can visualize that as fixed on the surface of Earth somewhere, and then there is a body frame which is attached to the body, and then about the body frame we discussed about several variables which we call as dynamic variables, which essentially consist of UVW and PQR. UVW are velocity components along body x, body y and body z, and then around those axes there are some rotation rates which are called roll rate, pitch rate and yaw rate. We have discussed that in detail before as well actually. And then we went ahead and derived this set of equations, which essentially consist of translational accelerations and rotational acceleration terms actually. And this consists of partly this Coriolis component and partly from gravity and partly due to external forces. Okay, and similarly we have these equations of for rotational rates and all that actually. So, we have done that in detail in the previous class. Now, if you see that there are some quantities theta phi especially here, which also vary with time, because that represents the attitude of the vehicle. Okay, so they are not fixed, so they keep on varying with time. So, we certainly want to have a rate of change of these variables as well. In addition to that, we also require this aerodynamic components here, this x, y, z and LMN, which are also functions of height, because they are functions of dynamic pressure, and dynamic pressure consists of density of atmosphere which varies with height. So, we need to have a rate of change of height actually, and especially if you want to have a trajectory of the aircraft, where it is going, what it is doing and things like that, if you want to visualize from some inertial frame, then we certainly need to have xy coordinates in the inertial frame as well. So, inertial xyz, the z part, negative z part of it will essentially give us the height part of it, the height of the aircraft at any point of time, and xyz together will define this coordinate of the CG of the vehicle, which will essentially give us the flight path trajectory. So, we need to have this phi theta. Along with that, we also need something called heading angle psi. So, we want to derive phi dot theta dot psi dot as well as x dot y dot z dot in the inertial frame actually. So, let us go ahead and try to do that. Those are called kinematic equations essentially. They do not rely on the external forces and moments, but they are actually velocity level equations. What we saw here is acceleration level equations. Okay. So, now let us continue with our derivation. So, here we need the concept of something called Euler angles, and later we will see that this is not the only parameterization. We can also have various other parameterization like direction cosine and quaternion, things like that. But let us complete the derivation with Euler angles actually. So, what you really want here? There is inertial frame, okay, here, okay, and there is a body frame out here. Okay. So, we want to know the orientation of this body frame x, y, z with respect to this inertial x, y, z actually. Okay, that is our objective here. So, what we really want to do, let us say first we want to take this in this coordinate system, just translate it over there, okay, then to try to rotate this coordinate system one at a time. Okay. First with respect to z axis, then with respect to y, then with respect to x, things like that. Ultimately, our aim is to this translated coordinate system should coincide with this body axis frame actually. Then whatever angles we require, those angles are nothing but this angle psi theta phi actually. Okay. So, let us try to understand a little better. So, first what we are interested is taking this coordinate system over there, simply translate that, and we have to have some different notation there, just not to get confused with that. So, this x dash or x prime, y prime, z prime is rewritten in terms of x1, y1, z1. This is simply just translated over there, nothing more actually. Okay. Now, this x1, y1, z1, I can rotate it with respect to the body x axis, with respect to the body z axis, okay, so that this entire xy frame, whatever xy frame was there previously, okay, it will try to coincide with this xy actually. Okay. So, this x1 y1 what you had by translating this inertial coordinate over there. Now, I will rotate it by angle psi with respect to the body z axis. Okay, z axis is your probably middle finger in your left hand side actually. So, this z axis you have to rotate it with z axis you keep it fixed and rotate it by angle psi, and that is what the picture says actually. Okay. So, that is what you will do, and the next what you will do is this rotated frame whatever is there you rotate it by angle theta about the y axis. So, first with respect to z axis, then with respect to y axis, and ultimately with respect to x axis phi. That is what you will do here. Okay. So, the sequence of rotations are psi, theta and phi, and this sequence of rotation is the translated inertial coordinate system which gets rotated about its axis actually. So, that ultimately it coincides with the body frame. Yeah. So, this is the concept actually. Now, let us try to see the relationship between them, and anytime you know the essentially what you are doing, we are actually doing a one angle rotation of a two dimensional axis frame at one point of time. Because about one axis you are rotating, so that particular axis remains fixed, and then the remaining coordinate system moves in one angle in 2D actually. Okay. So, let us try to see what is going on here. So, first we are doing that this coordinate frame we just translate there. Okay. So, essentially this whatever dots you have in the inertial frame, these are nothing but u1, v1, w1. Okay. This is simply translation. So, the velocity quantities do not change actually. But after that there is a rotation, and it is a 2D rotation, but we want to visualize that in 3D actually. So, w1 this particular picture if you see, that is the angle psi actually. Okay. So, this angle psi happens to take this u2 v2 to u1 v1. That means, whatever u1 v1 is there, okay, suppose you already have u2 v2, then what is u1 v1 actually. Okay. That relationship comes through this rotational 2D rotational matrix we know probably. So, and if you do not know, you can see some coordinate geometry book or something there, which is very standard. Okay. So, there are some neat properties out there. This for example, the determinant of this matrix is always 1. So, this matrix is never singular and things like that actually. So, this is actually an orthonormal matrix also, and there are various nice properties associated with that. But the fact is this suppose I have u2 v2 okay, after the rotation, then u1 v1 is related by that particular 2D matrix here with respect to u2 v2. And w1 is equal to w2. So, this becomes 0 0 and that becomes 0 0. So, you have 1 actually. So, this u1 v1 w1 is related to u2 v2 w2 that way. Then we have the next transformation by angle theta. Okay. So, this angle theta is with respect to u3 and w3, remember that, because y axis remains fixed here. Okay. So, v2 is equal to v3, okay, but the other variables u2 v2 w2 is related to u3 v3 w3 because of that actually, because of angle this rotation angle theta. And similarly, this x3 y3 z3 goes to xyz by angle phi ultimately. Okay. Now, this is a rotation about x axis actually, the transform x axis. So, all these rotation sequence of rotations, once you try to combine them, what do you combine? Let us say you want to have inertial rate of change of position, that means velocities, which is nothing but that is the definition in our, because the definition that we are talking about, the coordinate frame is x prime, y prime, z prime. So, I mean normally I prefer to write it as x I dot, y I dot, z I dot at the end actually. Okay, so, that is related, that is same as this, and this is nothing but same as this because of translation, right. That is how we started with, this is just translation here. Okay. But this translation is now given as that one, that is just the first translation. Then this translation what you see here is given by that is the second translation, second rotation thing. Okay. This is translation, this is first rotation psi, this is the second rotation and this is the third rotation. So, ultimately if you see the rate of change of position in inertial frame is related to phi theta psi all angles actually, okay, with respect to UVW. So, if you know UVW components, then x I dot, y I dot, z I dot is given by that actually, this entire sequence of rotation, and then you can simplify that. You can multiply all these three matrices and then find out one vector equation at a time actually. Alright, so that is about this position, rate of change of position in inertial frame. So, if I use this relationship, then I will be able to plot the vehicle trajectory actually in the inertial frame. Now, obviously, this is a function of phi theta psi, and then also we know that this is also a function of this u dot v dot w dot is also a function of theta and phi. So, obviously, we want to know this phi dot theta dot psi dot as well actually. Okay. So, how do they vary actually? Now, obviously, they are related to this body rate of rotations PQR. See, the phi theta psi is what? This inertial coordinate frame rotations in a sequential way, and PQR is nothing but the body rate of rotation about the body axis of the vehicle itself. Okay. So, in a vectorial sense, you can tell, okay, ijk is the body frame unit vectors. Okay. So, this w bar is I times p plus j times q plus k times r, which is also equal to, vectorially speaking, psi dot, theta dot and phi dot together. This is the same vector. There are two different coordinate system actually. This is written in terms of body axis, and this is written in terms of inertial frame actually, a sequence of operations essentially. So, vectorially speaking, these two are equal. Okay. Now, we have to try to find out what all goes in there. Now, vectorially speaking, psi dot is nothing but k1 times psi dot. Okay. So, remember this whatever we did here, this x1 y1 z1 stands for I1 j1 k1, x2 y2 z2 stands for I2 j2 k2, like that actually. Okay. So, in that sense, if you can see that this psi dot is essentially k1 times psi dot, because that is the first operation what we did actually. Okay. And essentially k1 and k2 remain same, because that is rotation about z1 axis. K component will remain same. Remember, ijk stands for x y z. So, k stands for z component, and there is a rotation about z axis. So, k component remains same actually. So, I can write it that way. Similarly, theta dot is essentially j2, because that is second operation, remember that. So, because it is a second operation, this theta bar dot is nothing but j2 theta dot, which is also equal to j3 theta dot, because that is the rotation about y2 now. Okay. And similarly, phi dot is like this actually. So, it is rotation about x3. Alright. So, this is how these vectorial notations can be decomposed to. Now, we have to simplify this k2, j3, I3, all sort of things. We have to put it in single framework, and then try to kind of see the relationship between them actually. Okay. So, if you let us do that, then what happens? This k2, okay, I can write it as something like this, I3 and k3 sort of thing. Essentially, you can write it into something like I2 and k2 as a function of I3 and k3. The way I have written it here, the below. So, this is what is written as j3 and k3 are related to j and k, like this. Remember, jk stands for body axis, and j3 k3 stands for just before that. Okay, last rotation is phi. Okay, so this relationship like that. Similarly, you can write it in terms of theta also. That means I2 and k2, theta is between x and z, remember that. So, I2 and k2 will be a similar relationship will pop up for I3 and k3. Okay, so that I need only the component of that, I need only the k2 component actually. So, I just taken out that one. Now, j3 and k3 are given like that. So, using this relationship, okay, this entire thing, whatever you have, see this vectorial dots, I can represent this like this actually, right. This is like k2 times I dot plus j3 times theta dot plus I3 times phi dot, if I want to do that. And then I kind of simplify all these, because k2 is like this, j3, k3 are like that. So, I put them together, and then that is ultimately equal to I times p plus j times q plus k times r. Now, that is where this we started with actually. Okay. So, I started with all these, okay, and then try to write all in terms of body coordinate frame, this phi dot, theta dot, psi dot, and that is equal to this I times p plus j times q plus k times r. So, now I can equate this component by component, because these three are orthogonal quantities. I, j, k are orthogonal to each other. So, I can equate these quantities component by component actually. Okay. So, let us do that, and then we will have this relationship. So, if you try to use this component by component, and then this relationship will pop up actually. Okay. So, vectorially speaking, I can write it that way. Okay. But normally, what we do not want PQR as a function of phi dot, theta dot, psi dot. We want the reverse one. We want phi dot, theta dot, psi dot as a function of PQR. That's the dynamics equation, right? That's what we want to integrate later. So, what do we do? I can take an inverse transformation here actually. Okay. So, this inverse transformation I can carry out, and if you sit down with this in inverse calculation, there is a 1 by determinant times at z matrix, and then you simplify all sort of things, then it will pop up like this actually. So, what you have ultimately, we have this xi dot, yi dot, zi dot, which will give us the trajectory part of it, and associated with that we have this phi dot, theta dot, psi dot also. Everything needs to be integrated together, because these are all coupled equations actually. Okay. So, and then this is not end of the story. We have this I mean you also see that these components we last class we just derived from simple logic, simple intuition. Now, can we do it in a formal way actually? So, what part of this will go to u dot, what part will go to v dot, and things like that. So, if you let us try to quickly do that, and this is essentially the same way. Remember, gravity is perpendicular to the, I mean parallel to the inertial z axis all the time, no matter whatever is the vehicle attitude. Gravity is always vertical with respect to surface of earth actually. So, that means it is always parallel to the z axis, it is always pointed to the center actually, earth center. So, that way this particular vector, now this need not be oriented with respect to body axis actually, body xyz. However, because this is orthogonal frame which spans this entire 3D space, so the g vector, any particular vector, and in particularly this gravity vector, I can decompose that into x, y, z components, and that is what I am doing actually. Okay. So, k1 times g, I am decomposing that in terms of I, j, k actually here. So, gx, gy, gz stands for the component of the gravity in body x, body y, and body z coordinate frame actually. So, what part goes where? That's the question actually. Okay. And also note that psi does not affect the component of gravity because k1 is equal to k2. So, anytime the vehicle takes a rotation parallel to the surface of earth, okay, that means with some psi rotation actually, then the gravity is still pointed vertically actually. That means the z vector, whatever it happens, it does not affect it. Gravity, in other words, the rotation psi does not affect the gravity components at all actually. Okay. Essentially under the flat earth assumption. I mean, if earth is flat, so if it takes some psi rotation somewhere, then it does not affect anything about the body x, y, z actually. So, we will not worry so much about that. What we really need is phi and theta components actually. Okay. So, they are essentially functions of phi and theta. Because at the moment there is a theta component, the pitch angle theta essentially these are, and phi angle is also roll angle actually. Okay. So, pitching and rolling essentially I mean they will make the components of gravity different in terms of x, y, z, but yawing does not normally affect it actually under the flat earth assumption. So, what you see here, your I3 is again I. Okay, that is ultimately your body axis. Okay, that is the final rotation, and then k3 is equal to this k times cos phi plus j times sin phi. Okay. So, and k2 is the other one. So, k3 and k2 is like this, it is a function of theta obviously, okay, right, and theta is related to I and k. So, phi is related to k and j, like that. So, if you do a proper bookkeeping, then k2 turns out to be something like that. However, k1 is equal to k2. So, that means you can substitute this relationship, and then you see that k1g, okay, is essentially like that actually. Okay. Whatever you see here ijk, okay, whatever components comes in I and j and k, these are body xyz components, and this is also body xyz component. Okay. So, if you equate the two, you get these things actually. Okay. And in last class we just derived it intuitively, but this is much more formal way of deriving it actually using this Euler angle rotations actually. So, this is how the entire Sextov equation is made of. But before going there, so previous lecture we have seen the dynamic level equations. Here we see the kinematic level equations, that means velocity level equations. These are angular velocity terms and these are translational velocity terms. Okay. So, this 6 equations coupled with the previous 6 equation what we saw that last class derives gives the complete set of Sextov equations. So, which is here. Okay. So, you see this consists of u dot v dot w dot, p dot q dot r dot, then phi dot theta dot psi dot, and x I dot y I dot z I dot. Okay. So, these 12 equations will derive that, and normally this height dot h dot is actually negative of z I dot. Okay. So, that is if you simply take out the last row and make a negative sign, then it will whatever pops up is nothing but h dot actually. So, that is not an independent equation. Okay. So, what is relevant here is only these 12 equations actually, And fundamentally speaking, this 12 equation gives this first 6 equations are directly related to the body axis only, and the last 6 equation gives a relationship between inertial frame and body frame actually, especially this phi dot theta dot psi dot. And then this xy dot, xi dot, yi dot, zi dot gives us the trajectory of the vehicle in the S seen from the inertial coordinate frame. Okay, so this is how it is all coupled together sort of thing. Now, this set of equation what you see here, these are Coriolis quantities. Okay, these are gravity and these are force quantities actually. And then I mean, if you go ahead and see that this is the C1 and C2, all these things we saw that last class also. Whatever C1, C2, C3, I mean all this C with a suffix, what you see here in P dot Q dot R dot equations are essentially functions of moment of inertia, which is given like that actually. We have derived that in the last class. Okay, rest of the equations are kinematic equations, so which are given here actually. Okay. And then this whatever you see, these components are actually this external forces and moments are the only ones which are different from vehicle to vehicle. All rest of the things are same, no matter whether a bird flies. Of course, bird has to be rigid body, which is not really true. But whether any flying object which is a rigid body, okay, which is governed by all the set of equations actually. Okay. The only difference comes is because of this external forces and moments. And that is where lot of study goes into in the aerodynamics study actually. So this is like aerodynamic component x, y, z, L, N, M, and x t, y t, z t, and L t and M t, N t are nothing but thrust components. So thrust components are not very difficult to visualize. It doesn't vary unless you have a thrust deflection mechanism, which happens in missiles and launch vehicles especially. With some fighter aircrafts, we have thrust deflection mechanism also for better maneuverability and all that actually. But normally this XY, this commercial aircraft sort of thing, these are fairly known actually. It all depends on engine power, how much you do, and what orientation you are fixed actually. That is where this phi t and psi t are coming actually. Phi t, psi t are not Euler angles, but they are the angles in engine orientation angles as fixed to the as seen in the body frame. Okay, with respect to the body frame, these engines are typically oriented by angle phi and psi for certain beneficial properties essentially. I will not talk too much on that. One thing that you can visualize is if it contributes something on the vertical direction, inertial vertical direction, then essentially it helps aiding to the lift to sustain the weight actually. Okay, so you don't really have to have a very big wing, okay, to sustain your lift. If thrust has a small component, let us say some sine of 2 degree or 3 degree, but thrust is a large quantity. So, that quantity multiplied by sine 5 degree also has a big quantity, which will aid to the lift actually in a way. So, like that there are various ways. Then they talk about jet should not hit the tail wing, so because the engine jet is there. So, it should never hit the tail wing actually, because a very unpredictable this circulation and all that. So, you want to have something like this way. So, the engine exhaust goes somewhere like that. It does not hit the vertical thing actually. Okay. So, there are various ways various reasons why these are all done that way. And then these aerodynamic forces and moments are typically generated two ways. One is there are 3 levels of doing that, 3 or 4 levels you can say. Aerodynamic forces and moments. First thing people do is just a first cut guess actually, which comes from first principles. That is something to start with. If you simply give the aircraft configuration, there are thumb rules available, basic relationships available, from which I can get a basic idea of what is there. Then it goes to the next level of what is called CFD actually, is computational fluid dynamics, where they talk about generating it in a grid point sense or for using finite element, finite volume, all sort of things. So, this will give you a little more better accurate sense. Okay, remember, these are not the flow pattern over this aircraft body is not very much in tune with whatever assumptions we do in the first cut model. First cut model is all clean configuration, there is nothing there, nothing objections are there, the surface is fairly good and all sort of thing. So, going to one level of higher, the CFD thing will account for all these protrusions actually. And then all sort of wing configuration, whether you have a fin out there, all sort of things it will take into account and try to give a better accuracy on that. Then it goes to the next level and people talk about wind tunnel study. So, this actually I mean, most of the time it is actually a model of this prototype. I mean, it's not a very big aircraft, you cannot put in a wind tunnel. So, you do a smaller version of that, and then try to see, instead of the vehicle flowing in the medium, now medium is flown over the vehicle. That means the air is flown over the vehicle, essentially the relative velocity matters there. So, you can get a fairly better accuracy ideas, I mean better idea about these forces and moments. But this wind tunnel study can only talk about generating what is called a static forces and moments actually. Dynamic level forces and moments it cannot generate. So, that means whichever the forces and moments that are components of these rates, rotational rates for example, PQR, those components cannot be predicted in a wind tunnel actually. So, for that you need the flight test. So, it goes through several rounds of refinement, okay, and then by meanwhile if your design configuration itself goes through refinement, again you do one more round of wherever you want to start, either from CFD or wind tunnel or flight test actually. So, that is where these models will keep on getting updated, okay. Then anything that is generated from flight test, that is essentially falls in the bracket of what is called parameter identification, because that is where you want to identify the how these forces and moments actually act on the vehicle. So, roughly speaking, this aerodynamic interaction of this vehicle is not very well understood actually from physics point of view. That is why we need to have several rounds of experimental study and then combine with a deterministic model to get a fairly accurate model. That means, this model what you are talking about, you can visualize that, so it is some sort of a hybrid model. One is deterministic part, there is a large component of that, there is a fairly equally good component of that which is aerodynamic dependent, which are somewhat theoretically understood, and there are components which are not understood, but then there are function fits from the experiments actually. Okay, so, that is largely data driven in that sense. Okay. So, all these things are part of the 6-stop model actually. Okay. Now, before you go ahead, there are some further comments. First thing is 6-stop model consists of 12 equations, out of which 3 equations are decoupled with the assumption that the earth is non-rotating and flat earth. Like what I told on the last class, if you see all these equations, essentially the psi actually and then xy do not come in any of the rest of the equations actually. So, psi and xy you can probably decouple that and tell, okay, even if there is actually 12 equations, under the non-rotating flat earth assumption, I can just work with 9 equations as far as local control design is concerned actually. Okay. So, and control design is typically local, it is a short duration stability problems and things like that, they are not long duration effects and all that. So, that is fairly okay. But also remember that one still needs to integrate this xy and psi equations to get the trajectory of the vehicle in your cell frame. Suppose you really want that, and trajectory information is essentially embedded in the guidance design actually. So, if you really want to talk about a proper guidance design, that means you take off from point 1 and go to point 2 and things like that, you really need this trajectory information. Okay. So, there you still need to integrate that, and there are better models available under this spherical earth assumption and then the rotating earth assumption and things like that actually. So, that is also there. So, okay, forgetting this factor, whatever 9 equations are there, this equation can be further reduced to 8 equations, because you tell, okay, locally the height does not change actually. That means that height dot, h dot, I still can, I just consider a reference height, and then h dot equation I do not have to integrate actually. Okay. I know what is my operational height, which height I am not talking about, and then I do not want to integrate this h dot equation. Okay. Height remains constant around that actually. So, then your the 9 equations become 8, and out of that 8 equation, we normally decouple that into 4 longitudinal equations and 4 lateral equations. Okay. These two we can visualize them as different actually. The weak coupling that exists between the two under this linearization approximation, we can neglect that actually, what I mean. Okay. So, these 4 equations are grouped together and other 4 equations are grouped together. I will talk about that of course, and then we tell, okay, this can be viewed that way actually. Then also remember that airplane is symmetry, that is one of the assumptions. So, that is why this cross moment of inertias are 0, and missiles and launch vehicles are typical symmetric about both xz plane and xy plane, and hence all the 3 cross moment of inertias are 0. Okay. Then also remember that this is not another story. In flight dynamics, people talk about various other frames. One of that is stability frame, the other one is wind frame. So, there are neat properties out of that, especially this, let us say this wind frame, the aerodynamic lifts and drag, they typically act on the wind frame. Okay. So, about this experiment, sometimes the wind tunnel data will be given in terms of stability frame. Okay. So, what is this? A stability frame is nothing but like a body frame. Okay. Just to rotate the body frame, okay, by angle alpha about the y-axis. Y-axis remains same. Okay. And then you rotate whatever xz axis by angle alpha. Okay. That will give you the stability frame. And wind frame is that stability frame you rotate further by angle beta, which is something called side slip angle. Okay, so it will perfectly align, the x vector of the wind frame will be perfectly aligned to the extreme velocity actually. Okay, so that is how you get the wind frame actually. So details I will not talk about, but again these are all rotations only. So rotation things are again this relationship will be reflected by this rotational matrix through this rotation matrix, that cos alpha in the diagonal and minus sin alpha and plus sin alpha in the off diagonal elements actually. Okay, so these are details and all you can find out in flight dynamics books, and one of the books is probably Stevens and Lewis with aircraft control and all that actually, aircraft simulation and control I believe. Alright, so let us move further and then we talk about, okay, what I just pointed out, can we discuss something called small disturbance flight dynamics. That means local effects. Okay, you do not talk about the nonlinear effect, everything coupled and things like that. So, can we do some sort of a decoupled motion, longitudinal, lateral and things like that with small disturbance assumption actually. And many of this material I will take it from this particular book, which is also I think very well written for these concepts. So, what you are doing, roughly what you are doing is all the variables, okay, whatever you had in the system of dynamics, you interpret that as perturbations around some nominal values. For example, u0, v0, w0, all sort of thing, these are all nominal values around which there are perturbations actually, delta v, delta w, delta w, all sort of thing. And the assumption is these perturbations are small actually. So, what you do, in the linearization, which I think we will not discuss yet, but one of the further classes we will discuss about that formally. So, in the Taylor series expansion, you neglect the higher order terms of these quantities actually. Okay, you have the 6 degree of freedom equation, that is a nonlinear coupled equation. So, you want to linearize this around some nominal operating condition actually. So, these variables with subscript 0 are operating conditions, and then this perturbation quantities you assume them as small and try and then put that in the Taylor series expansion and then neglect the higher order terms actually. Okay, you can do it in a different way also. I mean, if you see that book especially, it is done slightly in a different way, but that is okay. So, what essentially it does actually then? So, first you have to find out this operating point actually, like you need to find out what all these this u0, v0, p0, q0, all sort of things actually. So, for that there are various steady state conditions available, which is called trim condition actually. And trim does not necessarily mean straight and level flight, but that is one of the very typical trim condition. If it goes straight and level, that is actually like a steady state condition, which is essentially called a trim condition actually. Yeah. Okay, but there are various other trim conditions also available. Okay, trim condition means nothing changes, your control surfaces and all that are reflected by a constant quantity. Okay. Then suppose you want to take a vertical loop, okay, it can also be considered as a trim, okay, horizontal circles and all that can also be considered as a trim and things like that. But most popular thing is straight and level flight. If I just go straight and level and then do some stability analysis around that actually. Okay. Alright, so what we assume here is straight and level flight. All these V0 and PQR zeros like P0, Q0, R0, these are rotational rates. V0 is the velocity component along body Y. Okay. So, these quantities are all 0 and these are like force quantities in the y and z direction coming out of thrust actually, and typically these are true for all time. So, body y and z component, thrust does not contribute any component largely, especially in commercial flights actually. Okay, so then so under these assumptions, okay, you select these quantities, that means you tell, okay, what is my thrust level, thrust force, there is engine, I want to operate in 5% of thrust, 10% of thrust, 15% of thrust, whatever it is, the maximum thrust what I mean. So, you fix that thrust quantity and then fix what height you want to fly, let us say the vehicle flies. So, once you do this, that means all these variables are either 0 or known. Okay. Then you want to enforce, remember these 9 equations are there for us. Okay. So, all these 9 equations should I mean the rate of those variables should be 0. There is no I mean this rate of change actually for all these u dot, v dot, w dot, also p dot, q dot, r dot, phi dot, theta dot and zi dot. This is the height part of it actually. Okay. So, all these quantities if I force it to 0, this will essentially give me various free variables, and out of these free variables I know these, okay, and I have to find out this actually. And remember, this is just one way of finding the trim condition. There are other ways also basically. So, what I mean essentially you are somehow making sure that this happens to be 0, all these rate of change happens to be 0 actually, and then you solve for that. Okay, and in that process you can also verify that what you really get, okay, that also has to be 0 actually. Okay, all right. So, you just verify that there is no force from aerodynamics, y has to be 0, no moments also from aerodynamics about the body axis actually. That is just verification. I mean, if that does not satisfy, then there is something wrong here actually probably. You can go back. So, you solve this. So, essentially what I mean is all these variables with subscript 0 are now available actually. Okay. Now, you can take, okay, this aerodynamic forces and moments, this perturbation around that, okay, I can visualize in Taylor series expansion, and I want to keep the major components only. Okay, and this series does not stop actually. Suppose somebody wants to write this is other functionalities actually, then they can still write it. But as far as perturbation in delta x is concerned, remember this delta x is the aerodynamic force in body x direction actually. Okay. And then this aerodynamic force can be function of u, function of delta w, function of delta e, function of delta thrust, all sort of things. Okay. And this series can be expanded also. Okay. But these are the major components actually. By the way, this way of writing is something called component build up actually. Okay. So, component by component you are building up whatever components come here ultimately actually. Okay. Similarly, delta y you expand and delta z you expand, and delta l, delta m, delta n also you expand actually. Okay. Then you can write this. Okay. Then the interdependencies, if you see, okay, out of that, see, if I club these variables together, delta u, delta w, delta q and delta theta, they become independent of rest of the equation. They become only functions of themselves and these two quantities, delta e and delta t actually. Okay. So, essentially I will be able to write this x dot equal to x plus vu, what we know, I mean state space equation form basically. So, linearized state space equation form for longitudinal dynamics happens to be like that. It is a 4-dimensional system where state and control are defined like that, and for notational simplicity these are also defined that way. Okay, xu means this del x by del u with 1 over m normalization, that is well, acceleration quantity. X is a force quantity, but xu which is acceleration quantity actually 1 by m. So, it is the force divided by m becomes something like acceleration quantity basically. Anyway, so with these notations intact, all this whatever you see here in the matrix will turn out to be like that. So, in flight dynamics, suppose somebody gives us this A and B matrix numbers, these numbers essentially mean these quantities actually. So, that means they are coming from there, and these, right. So, that's the thing, and it is there nice consequences actually. Now, I can further divide this 4 by 4 into two 2 by 2 systems. Okay. And then I will take, okay, one time I will talk about this delta u, delta theta together, okay, out of that delta u and delta theta together. Other time I will consider delta w and delta q together in a way. They are all large, okay, which is a function of what and things like that. I mean, that's what it turns out. And there are two types of nice perturbation happens actually in the study around the steady state level flight. So, one thing is which is called as phugoid mode. Essentially, the aircraft drops its height to a significant thing and then goes off actually. The vehicle attitude does not change, okay, attitude remains same. The entire vehicle will keep on going and then coming down and then go, it's like a roller coaster ride actually. Okay. So, this happens with something like constant angle of attack actually. Okay. So, under these assumptions, delta alpha becomes 0 because alpha remains constant, and then because delta alpha is defined that way. So, delta w also becomes 0. So, you are left out with this nice small matrix and homogeneous linear system which you can analyze it very clearly. This is a second order system in a way. Delta u and delta theta just analyze together basically. So you can find out the eigenvalues, and then you can tell, okay, you can write it as a second order equation, and then tell, okay, this s square plus 2 zeta omega n s plus omega n square equal to 0, that kind of equation you can write, and tell, okay, this omega n turns out to be like that and zeta turns out to be like that. So in the figured mode, there is a natural frequency and there is a natural damping, okay, which are actually given like that, and the motion is something like that. Okay, it will go to a maximum speed at the down, then it will again pick up, and then there is a minimum speed at the top. Okay, then it will come down and it will proceed. This is a nice roller coaster ride actually. Obviously, nobody in the passenger aircraft will like that. So you want to control that also basically. Okay. Now similarly, there is another motion which is called short period. That means this does the vehicle doesn't go through a large amount of height variation. However, there is a vibration around that. So this happens to be, okay, this happens to be something like this actually. Okay, so this this oscillation, oscillation about this vehicle y-axis sort of thing, but this is actually a little more unpleasant experience actually for the passengers. So what happens there is a change of angle of attack, and this oscillation, okay, fortunately happens to be heavily damped actually. So that means these oscillations typically die out fast, and some of these you might have experienced while commercial flights. Sometimes this wind gust and all that, they naturally die down actually also without too much of control action. Control can be excited also for that. But suppose then the damping is not satisfactory, then obviously we need a control for that also. And both of these are actually controlled by elevator actually. You have elevator, aileron and rudder. So these are longitudinal motions, okay, and these are functions of elevator actually. Okay. Delta E, remember that here. Okay. So this delta E quantity, what you see here, is actually largely utilized for suppressing these two phenomena actually. Okay. So this is again short period mode. So again you can you can visualize the dynamics in terms of delta W and delta Q, again a 2 by 2 matrix. Again you can do this natural frequency and damping ratio actually. It happens to be like that. And remember, these are all functions of aerodynamic parameters, which are also functions of vehicle configuration. Okay, so like that actually. Now similarly, in the lateral dynamics, you can decompose that into again 4 more variables, which are not same as the other variables. Here you talk about V, P, R and phi. Phi is the roll angle name of that, and then the A and B matrices are given like that. Okay, all these parameter values and all. And similarly, because if it is Ix, Z is also 0, which happens to be in missiles and all that, then this whatever you see here, it will further reduce to this rather simple looking form. Okay. And this will turn out to be like that actually. Okay. So aircraft response, as far as that is concerned, you can see that in this lateral dynamics there are 2 modes again. One is spiral mode, another is rolling mode, and there is a Dutch roll motion also, which is a couple between these two. So let us see what is that. So this is spiral mode, directional divergence first. So what it does is, this doesn't possess too much of directional stability. So in other words, there will be a increase of this side slip angle beta. So the UVW component, remember that. So the V component starts building up actually. Okay, if the V component starts building up, then the vehicle will largely deviate from its intentional path. In a long duration, it is supposed to go in that direction, but it will not go there. It will try to deviate that. And then at some point of time, beta will couple with phi, and then roll dynamics will start, all sort of things actually. Okay. So that is what is called directional divergence. The other one is spiral divergence, which is actually largely responsible from this gradual spiraling motion actually. That means the rolling stability, suppose the vehicle starts rolling and all that actually. Okay, then it will also lead to yaw, that we know that. The moment the vehicle rolls, it yaws also. So if that is not stable, then it will excite a spiral mode. That means this radius of curvature becomes very fast, and it also loses height and it crashes actually ultimately. So these two are actually, directional divergence is not that bad. In other words, if it is not controlled in time, then it will lead to further bad things. But this is even more further bad in the beginning itself, because it this spiraling action gets amplified very quickly actually. Okay, so then this particular aspect is largely controlled by rudder, and this particular effect is largely controlled by ailerons actually. Remember, it is a motion due to phi. roll angle. This is a motion due to beta. Okay, so beta is side slip angle. So beta is controlled largely through rudder, and roll is largely controlled through ailerons. Okay. So then there is a nice coupling with the two. Okay, this is what is called Dutch roll oscillation. So here it will the directional and spiral oscillations will be coupled together actually. It will roll, and hence beta will build up. It will go somewhere. Then it will stabilize. I mean, it will start in opposite direction sort of thing, and then it will go like this, and then it will go like that, and this keep on. Remember, this amplitude keeps on building also. And this typical name comes from this ice skating actually. Okay, when you do ice skating, this is one side you go something, and then you come back to the other side and things like that actually. So that is typically does people like that, ice skating and all. So that is how it the terminology has been given actually. So time period can be of 3 to 15 seconds, and then typically this yaw damper is used. Yaw damper is largely by the way you design the vertical fin. The part of the vertical tail which is ahead of the rudder, that vertical fin, if you define it properly, if you design it properly, then that will cause the proper yaw damping actually. But in addition to that, you can always control it using both aileron and rudder together, because this motion you cannot decouple into two 2x2 system. You have to talk at least about one 4x4 system. Okay, and then where this both aileron and this one rudder will come, and hence you design them together. That's the power of this state space design approach. You talk about the coupling effect also in the design process actually. Okay, now before we stop this class, I will also take you through some various attitude representation, which assesses this entire 6-DOP and all we derived in terms of Euler angles, but there is a strong drawback for that, and we will see that, and then there are also alternative attitude representation people have thought about seriously actually, and these problems are further amplified if you have this satellite control problem, for example, or missile dynamics, which have large angle of rotations coming into picture. Okay, so satellites can tumble, it can completely turn 360 degrees and keep on doing that in space. And hence the missiles also, they are high angle of attack maneuvers, you can take quick turns and all that. So large angles when you talk about, these Euler angles are typically not good actually. So we have to have some other thing. So let us see that. So attitude representation by definition is essentially the attitude coordinates are set of parameters that completely describe the orientation of a rigid body relative to some reference frame. And one set we have already seen, Euler angles. The other thing that are available to us is direction cosines and quaternions. In fact, direction cosines are the first step before even Euler angles. And then it does not stop here. The people talk about Rodrigues parameter, then modified Rodrigues parameters, and the family of that actually. There are give and takes actually. Okay. So broad class, all these parameters what you see, there are two broad classes. One is like a 3-parameter representation, and another is a 4-parameter representation. Essentially, quaternions fall in that 4-parameter representation. So 3-parameter representations are nice, because the attitude is actually a 3-parameter representation. Whatever you see, any attitude is 3 angles somehow. Okay, but there is a serious problem. Okay, we will see that. And then and especially, okay, if you want to quickly look at that, I can also go there and come back probably. See this Euler angle representation, if you see it here, there is a tan theta term involved. Okay, right, what you see here, and tan theta is sin theta by cos theta, and here is a sec theta which is also 1 by cos theta. So that means if theta goes to 90, then the cos theta becomes 0, and there is something divided by 0, which means these rates will go to infinity. That is something called Zimmer-Lock actually. That means no matter whatever degree of accuracy you use, delta t, take it to very small quantity, even then the integration cannot be done. This dots go to infinity. The angles are okay, the angle values are fine, but the rate of change goes to infinity actually, which is not nice. So this set of, and this rate of change is actually a function of the sequence of rotation. How you do that? You did that sequence of rotation from psi theta phi. If you do a different set of equation, then the variable with some tan theta will happen to be tan phi or tan psi. Okay, somewhere you will be getting locked actually. So there is no way you can get out of this mechanism actually. Okay, so that is where it happens, and this is actually bad because it happens in 90 degree. 90 degree is a small angle. Now the whole idea of this MRP and all that, modified Rodrigues parameter, they have already taken into something called 360 degree or multiples of 360 degree. Then only you will have singularity. So one full round you can take, and then still can avoid singularity and all that, and you can still talk about 3-parameter representation, which is nice. Okay, 3 to 3 is actually like there is a, I mean this redundancy variable does not come into picture actually. So, that is why. So, let us talk about that now and then okay. So, first is direction cosine. So, direction cosine is if you have a reference frame, okay, and if you have a vector, any vector, I can talk about direct angles actually, right. This vector whatever I have, I can take direct angles with respect to these axes, okay. And if I take cosines of those angles, okay, and put them in a matrix form, then this is the matrix that I am talking as direction cosine matrix, okay. Understood? That means the components of this vector, whatever this vector, this something like a B1 component, B2 component, B3 component, each of the components, what I mean, they will have direct angles with respect to this other frame. See, there are two frames, one is N frame and one is B frame, okay. You can visualize the N frame as inertial frame and the B frame as body frame, okay. So, each of the components of the body frame makes an angle with all the 3 axes of the inertial frame directly. So, that means you have 9 such equations actually, okay. So, 9 such representations actually. So, all these things if I put them together, then the B frame is related to the N frame through a matrix representation, which is directly like cosine, I mean the cosine terms and all that, we know that. If you take dot products and you can derive it actually, that is not a problem. The two vectors, if you take dot product, that the cosine angle will come into picture, and that is why these cosine terms come actually, okay. So, this B, what results from this algebra is something related to N through the C matrix, and C matrix is essentially called direction cosine matrix. That's the definition actually. Now, remember we really require 3, but you have 9 parameters actually. That means there are 6 redundancies here. That's the problem here actually, okay. Now, before doing that, before we even talk about that, let us observe some nice properties, that C is essentially an orthogonal matrix. An orthogonal matrix has a nice property, the C times C transpose is actually identity. That means inverse of this matrix is transpose, and inverse always exists, okay. So, there are nice properties of that actually, okay. Inverse is transpose and determinant of this is always plus or minus 1 depending on what angles it takes. And as I told, direction cosine is probably the most fundamental, most natural way of visualizing things, but it is also highly redundant, and because of this we require 3, but it has given us 9 parameters actually, okay. So, 9 entries. So, 6 extra parameters are redundant through this orthogonality condition basically, okay. Orthogonality condition tells us that each of the vector, this vector is orthogonal to that and this vector is orthogonal to that, and because this vector matrix is orthogonal, the vectors are also orthonormal. So, if I take dot products of any 2 rows actually, they are zeros, and if I take norm of any row, that will happen to be 1, okay. These are orthonormal, each of the vectors are orthonormal to each other actually, okay. So, those are the redundancies that I am talking. So, you have this combination sense, 3 combinations of dot products and then 3 normalization quantities actually, okay. So, these 6 redundancies you have to talk about actually, okay. Now, Euler angles, we have discussed everything on that probably, but still to visualize that, the standard set of Euler angles is what we have done. It is a psi theta phi rotation actually, okay. But this is also called asymmetric set. What people use in satellite dynamics and all is what is called a 3-1-3 set of rotations actually, okay. So, this will not talk too much on that anyway, but that is also called something called symmetric set actually, okay. You do not have to rotate it using this 3 to 1 actually, you can also go for 3-1-3. 3 means 3 stands for psi, 2 stands for theta and 1 stands for phi. So, what you are talking here is psi, phi and again psi, okay. You can also do that actually, that is typically standard for satellite dynamics and all. And then okay, there is a direction cosine matrix can be parameterized in terms of Euler angles, we will see that relationship also. And obviously, Euler angles define successive rotations and all, we discussed about that. So, this is the representation actually, like if you have Euler angles, theta 1, theta 2, theta 3, I am not writing in terms of theta phi psi, you can also write in terms of 1 to 3 notation actually, theta 1, theta 2, theta 3, then the direction cosine matrix turns out to be like that, where C theta stands for cos theta and S theta stands for sin theta especially. Then, once you do that, then this psi theta phi can also be given in terms of inverse transformation, that means somebody gives me the direction cosine matrix, then I can also recover this Euler angle quantity. So, there are back and forth transformations available actually, okay. If once you know one representation, you can find out the representation in another one actually, Okay, so then finally let us talk a little bit on quaternions. Quaternions is essentially to get rid of the singularity problem. Now, unfortunately, what happens is anything that you use, either you direction, cosine, Euler angle, modified Ortiz parameter, whatever you use, all these 3 parameter representation do suffer from singularity. It is a matter of where the singularity occurs, but it has a singularity. Now, can you talk about singularity free transformation, and that is where this quaternion algebra is useful actually. So, what it turns out, we will come back to this probably, but that is the fundamental thing is something here. So, for every attitude change that I am talking about, I can always visualize some axis somewhere around which I can take one rotation and finish it off. Okay, this is for all the sequence of rotation that I am talking from inertial to body, whatever, one axis frame to other axis frame, there is one vector, what is called the principal rotation vector, around which I can take one rotation, so that these 2 axes will merge together actually. That is the concept. That is the theorem actually. Okay. Now, obviously, we have to design that axis frame, and that is given by 3 quantities Q1, Q2, Q3, and then there will be something like one rotation quantities also you have to discuss about. That is the quantity phi actually. So, quaternion will consist of 4 parameters Q0 and then Q1, Q2, Q3. Okay, Q1, Q2, Q3 will typically give some sort of something like a direction of this rotation vector, and then the phi angle which you can take out from this Q0 component actually. Okay, phi by 2 is cosine inverse of Q0 basically that way. This phi angle is a rotation about that vector which will make it coincident actually, all the thing. Now, going back to that, this is the quaternion form, this Q0 plus Q bar consists of Q1, Q2, Q3, and then there is a, I mean this ijk, you can see that there are the square of that, and I times k times a all equal to -1. There is some neat algebra associated with that actually. Okay. So, you can see some of these, and equality sense also, like there are various further things. I think some of you who are interested in this, you can see this particular book which I have taken it from actually, Analytical Mechanics and of Space System. There is a nice chapter for doing all this actually. Okay, so anyway, so coming back to this, so addition you can define it that way. Suppose you have 2 quaternions, let us say P and Q. So, P will have P0 plus P1, P2, P3, Q will have Q0 plus Q1, Q2, Q3, and then with respect to that you can define addition, multiplication like that actually. Then there is a conjugate quaternion which is negative of all these quantities, and the norm of the quaternion is defined like that. Okay. So, obviously, this Q square, this whatever you see here is actually 1. Q0 square plus Q1 square plus Q2 square plus Q3 square happens to be 1 actually. That is called unit quaternion. Okay, so that is actually a restraint, that is a constraint that you have to operate with actually. So, all these parameters, this has to satisfy that, and that happens to be a problem in numerical integration, for which we need to normalize it forcefully, and for which there is no unique way of doing that. That is the difficulty there actually. Okay. So, quaternion also satisfy this quaternion 2 Euler angle. Suppose you know Euler angle, then you can find out quaternion. Suppose you know quaternions, you can find out the direction cosine matrix, things like that. There are transformations available which you can extract one information from the other actually. So, I request you to see some of these chapters for more details. Okay, this is a control theory class, so we cannot talk too much detail on that, but with all sort of these flight mechanics ideas and all that, we will be able to utilize our control theory ideas for flight control and guidance design actually. That is my motivation. So, with that I will probably stop this class. Thanks for the attention.